In this article, we learn about how can we convert the first order, first degree differential equation in reducible to homogeneous form. So, an equation of the form dy by dx equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2, where a1 upon b1 not equal to a2 upon b2. So an equation of the form dy by dx is equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2, where a1 upon b1 not equal to a2 upon b2. There are two cases. Number one, if c1 and c2 both are 0, then above equation is in homogeneous form, and it can be solved by substituting y is equal to vx. Now we take second case. If c1 and c2 are not both 0, then above equation, then by changing variables, the above equation reduces to homogeneous form, and constants c1 and c2 becomes 0. So here, if any of the equation of the form dy by dx is equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2, where a1 upon b1 not equal to a2 upon b2. So if c1 and c2 both are 0, then this equation is homogeneous form, and it can be solved by substituting y is equal to vx. यदि कोई फर्स्ट ऑर्डर फर्स्ट डिग्री की डिफरेंशियल इक्वेशन इस फॉर्म में गिवन है dy by dx is equal to a1x plus b1y plus c1 upon a2x plus b2y plus c2, where a1 upon b1 not equal to a2 upon b2. If these constants c1 and c2 both are 0, then this equation is in homogeneous form, and it can be solved by substituting y is equal to vx. In the second case, if c1 and c2 are not both 0, then by changing the variables, the above equation reduces to homogeneous form, and constant term c1 and c2 becomes 0. No, so by putting x is equal to capital X plus h and y is equal to capital Y plus k, where h and k are constant. Here for changing the above equation in homogeneous form, we put always x is equal to capital X plus h and small y is equal to capital Y plus k, where h and k both are constant. Now we differentiate this with respect to capital X, we get d small x is equal to d capital X because h is constant, and d small y is equal to d capital Y, and k is constant, so differentiation of k and h is 0. Now we know that when dy by small dy by small ds can be written as d capital Y upon d capital X is equal to a1. In place of x we write capital X plus h, in place of y we write capital Y plus k, and then constant c1 divided by a2. In place of x we write here capital X plus h, in place of y we write here capital Y plus k plus c2. Now the numerator can be reduced a1x plus b1y plus a1x plus b1y plus a1h plus b1k plus c1, and the denominator can be reduced a2x plus b2y plus a2h plus b2k plus c2. Now h and k choosing such that a1h plus b1k plus c1 is equal to 0 and a2h plus b2k plus c2 is equal to 0, then above equation can be reduced. Then above equation can be reduced into d capital Y upon d capital X is equal to a1 capital X plus b1 capital Y divided by a2 capital X plus b2 capital Y, and this is homogeneous. So by substituting y is equal to vx, so by substituting y is equal to capital Y is equal to v capital X, we can solve above equation. So if any of the equation of the form dy by dx is equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2, where a1 upon b1 not equal to a2 upon b2. There are two cases, case 1 and case 2. If these constants c1 and c2 both are 0, then this above equation can be reduced in the form dy by dx is equal to a1x plus b1y divided by a2x plus b2y, and this is the homogeneous form of first order and first degree, and it can be solved by substituting y equal to vx. In the case second, if c1 and c2 are not both 0, then by changing the variable x and y, we can convert this differential equation into homogeneous form. So, and the constant c1, c2 becomes 0. So by putting small x is equal to capital X plus h and small y plus is equal to capital Y plus k, where small h and small k both are constant. So we differentiate this small h with respect to capital X and small y with respect to capital Y. So we get here d small x is equal to d capital X and d small y is equal to d capital Y. Now we put here d in place of d small y, we put here d capital Y, and in place of d small x we put here d capital X, and in place of x and y we put here capital X plus h and capital Y plus k. Now we solve this, so we can convert this a1x plus b1y plus a1h plus b1k plus c1 upon a2x plus b2y plus a2h plus b2k plus c2. Now choosing h and k such that here the constants h and k choosing such that this constant term a1h plus b1k plus c1 and a2h plus b2k plus c2 is equal to 0. When these constant term becomes 0, So this differential equation dy by dx is equal to a1 capital X plus b1 capital Y upon a2 capital X plus b2 capital Y. So this is the homogeneous. So by substituting y is equal to vx, we can solve above equation. Now we take some example. Now we take here some example. Solve the equation. Solve the equation 2x plus y minus 3 dy is equal to x plus 2y minus 3 dx. So this equation can be written as dy by dx is equal to x plus 2y minus 3 divided by 2x plus y minus 3. Now we comparing this equation by a1x plus b1y plus c1 divided by a2x plus b2y plus c2. So we can see here a1 is equal to 1, b1 is equal to 2. Similarly a2 is 2 here and b2 is 1 here. So we can see here a1 upon b1, that is 1 upon 2, and a2 upon b2, that is 2 upon 1. So we can see here a1 upon b1 not equal to a2 upon b2. So this is the equation. We convert this equation into homogeneous form by changing the variables. So put here small x is equal to capital X plus small h, and small y is equal to capital Y plus k, where h and k are constant. Where h and k are constant. Now here choosing h and k such that a1 h, choosing h and k such that h plus 2k minus 3 equal to 0 and 2h plus k minus 3 equal to 0. Here we choose the constant h and k such that in the numerator, in place of x we put h, in place of y we put k. So it is h plus 2k minus 3 equal to 0, and the second equation can be obtained by putting x equal to h in the denominator and y equal to k, and we get two equation 1 and 2. This is the first order first degree differential equation. Here constant h and k choosing such that in the numerator we put in place of x we put h and in place of y we put k, we get the equation 1. Similarly in the denominator in place of x we put h and in place of y we put here k and get the equation 2nd. Now we solving these equation 1 and 2 and get values of h and k. So equation 1 multiplied by 2, so we get here 2h plus 4k minus 6 equal to 0. Suppose this is third equation. Now solving this third and 2, so we subtract equation 2 from third. So we write here 2h plus 4k minus 6 equal to 0 and 2h plus k minus 3 equal to 0. Now we subtract, this is minus minus, this is plus, so this is cancel out. 4k minus k, this is 3k minus 6 plus 3, so this is minus 3 equal to 0, so we get k is equal to 1. Now we put k is equal to 1 in any of the equation 1 and 2, we get value of h. So h plus 2 multiplied by 1 minus 3 equal to 0, so h plus 2 minus 3, so h is equal to 1 here. Now we can see here small x is equal to capital X plus 1 and small y is equal to capital Y plus 1. So we can see here d small x is equal to d capital X and d small y is equal to d capital Y. We differentiate this small x with respect to capital X and small y with respect to capital Y. So differentiation of 1 is 0 because it is constant. So we can write d small y upon d small x is d capital Y upon d capital X. And in place of small x we put here capital X plus 1. In place of y we put here capital Y plus 1 and minus 3. Divide by, this is 2. In place of x we put here capital X plus 1. In place of y we put here capital Y plus 1 minus 3. So d capital Y upon d capital X, this is equal to x plus 2y plus 2 plus 1 3 minus 3, this is cancel out. And in the denominator here 2x plus capital Y and 2 1 are 2 plus 1 3 minus 3, this is cancel out. So we can see here the given equation reduced to in homogeneous form, because here f1xy and f2xy both are homogeneous in same degree. So we solve this differential equation by putting y capital Y is equal to v capital X. So d capital Y upon d capital X is equal to v plus x dv upon dx. You can see here by the substitution, in place of small x we put here capital X plus 1, in place of small y we put here capital Y plus 1. We can see here the above equation reduces to homogeneous form. Now we solve this homogeneous form by substituting capital Y is equal to v capital F. Now we differentiate this with respect to x, so d capital Y upon d capital X. In the right there are two functions, so first we write v and differentiation of x with respect to x, that is 1, plus second function that is x and differentiate v with respect to x, so we write here dv by dx. So in the above equation, in place of d capital Y upon d capital X, we put here v plus x dv upon dx is equal to x plus 2 y is equal to v x divided by 2x plus vx. Now from the numerator and denominator we can see here this x is common and cancel out, so it becomes 1 plus 2v upon 2 plus v. Now in the left hand side there is v, so we transform this v on the right hand side, so we get here x dv upon dx is equal to 1 plus 2v upon 2 plus v minus v. Now here we taking LCM, so that is 2 plus v, so we get here 1 plus 2v minus 2v minus v square. So this plus 2v minus 2v is cancel out, so we get here x dv upon dx, this is equal to 1 minus v square upon 2 plus v. Now we convert this equation in, variable separable form. So we convert here this equation in variable separable form. So we can see here this can be written as 2 plus v divided by 1 minus v square dv is equal to dx upon x. Now we can see here all the terms of y contained with dv and in one side, and dx and all the terms of x in the other side. So this is variable separable. Now we integrate both the sides. Integrate both sides. So we write here 2 plus v divided by 1 minus v, and this is 1 plus v. Here we factorize this 1 minus v square is equal to integration of dx upon capital X. Now we do partial fraction of 2 plus v upon 1 minus v and 1 plus v. So this is a upon 1 minus v plus b upon 1 plus v. Here we do partial fraction of 2 plus v upon 1 minus v square. So it can be written as a upon 1 minus v plus b upon 1 plus v. Now we taking LCM on both the sides, so we get here 2 plus v is equal to a multiplied by 1 plus v plus b multiplied by 1 minus v. Now we put here 1 plus v is equal to 0, that is v is equal to minus 1. So we get here 2 minus 1 is equal to a multiplied by 0 plus b, 1 minus v is equal to minus 1, so it is 1 plus 1 2, so 2 minus 1, this is 1 and this is 0 and 2b, so from here we get b is equal to 1 by 2. Now again we put 1 minus v is equal to 0, so we get v is equal to 1, so 2 plus 1 in the left hand side, in place of v we put here 1, in place of v here we put 1, and here 1 minus v is equal to 0, so 2 plus 1 3, and this is 2a and this is 0, so here a is equal to 3 upon 2. So we put value of a and b and then integrate here. We can see here this 2 plus v upon 1 minus v, 1 plus v is equal to a upon 1 minus v, and a is equal to 3 by 2, so we write 3 upon 2 1 minus v, and b is 1 by 2, so this is 1 upon 2 1 plus v, dv is equal to d capital X upon capital X. Now we integrate this, so this is 3 by 2, so we taking this is constant, so it will be outside the integral sign. Integration of 1 upon 1 minus v, this is minus times log of 1 minus v, and here 1 by 2 is constant, so it will be outside the integral sign. Integration of 1 upon 1 plus v, this is log of 1 plus v. On the right hand side, integration of 1 upon x is log of x plus, here we taking constant, that is 1 upon 2 log c. Now we multiply whole of the equation by 2, so we get here minus 3 log of 1 minus v plus log of 1 plus v is equal to 2 log of x plus log of c. Now we solve both the sides, so we get here this is log of 1 plus v divided by 1 minus v whole cube. On the right hand side we write here cx square. So this can be written as 1 plus v is equal to cx square multiplied by 1 minus v whole cube. Now we put here value of v, that is capital Y upon capital X is equal to cx square 1 minus capital Y upon capital X. Now we solve the left hand side and right hand side taking LCM capital X, so we get here x plus y is equal to c of x minus y whole cube. So and here x plus y is equal to c times x minus y whole cube. Now we put value of capital X and capital Y in terms of small x and small y. So we get here x plus y, that small x capital X plus capital Y, that become x plus y minus 2, and the right hand side when we subtract y from capital X, we get here small x minus y whole cube. So this is the solution of the given differential equation of first order first degree in the form dy by dx is equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2. Thank you.